Hi, in this video we are going to see an introduction to P and NP problems. Let's start with this introduction of computational complexity. For any algorithm, we are going to have two complexities. One is space complexity and another one is time complexity. So space complexity will deal with the resources required to save the programs and to save the data record for the program. But in the case of computational complexity, it deals with the running time. So how much time it is taking to compute and find the solution for the problem is given by computational complexity. Some of the algorithms will provide polynomial time solutions to solve problems, but some of the problems like Turing machine's halting problem is not solvable by any computer, and no matter how much time it is given, right? So let's see what is halting problem. So this halting problem is just to check whether the given problem P will be halted or not, right? So that is given by this function stop. So if stop of P, we can write, if the program is stopped means, then we can say the program halts. Otherwise, the P doesn't halt, right? So this is what the function. So this halting problem cannot be decided, right? Decidable whether it will be stopped or not, as the given input program may be of any type, right? So there are two types of problems. One is optimization problem and another one is decision problem. So the optimization problem helps you to find the optimal solution for the problem, but decision problems helps you to find whether there exists an optimal solution for the given problem. So if you are finding the minimum spanning tree for a graph, then it is known as optimization problem. If you are checking whether there is a minimum spanning tree for a graph, then it is known as decision problem. Similarly, for Hamiltonian circle, if you are checking whether it is available, then it is known as decision tree. But if you are finding what is the Hamiltonian cycle for the graph with the minimum weight means, then it is known as optimization problem. So some of the problems can be solved in polynomial time, but some of the problems cannot be solved in polynomial time. So normally this optimization problem will be in the form of exponentiation. So let's see what are the ways to solve this problem in polynomial time. Before going to see this in detail, we are going to see some preliminaries of languages. So what is a language? A language L is a set of strings made up of symbols from a set of values or meta symbols, right? So the meta symbols, for example, here if you are giving 0 or 1, so we can make any set of combinations of symbols using these zeros and ones, right? So a language L, which is representing all the primary numbers in binary form, is given in this example. Here we are creating 10, 11, 101. These are set of strings formed for this set L, and when you are finding the decimal equivalent, it is 2, 3, 5, 7, 11 like that. Okay, so all these strings are formed by either 0 or 1. So to find the string, we need some of the operations on language. So let's see one by one. First, we have to see what is empty string. Normally, the empty string is represented by epsilon and the empty language is pi. The operations complement of a language L is given by L dash, which is, for this given example, the complement of 0 is 1 and the complement of 1 is 0. And similarly, for the decimals also, we can say complement of 9 is 1 and complement of 7 is 2, like that, right? And in the case of concatenation of two languages, it means you are going to take symbols from language L1 as well as from language L2. Just x1 and x2, both the things we are taking. x1 is from L1 and x2 from L2. And union of two languages represented by L1 union L2, which is you are going to take either the language symbols from language L1 or from language L2. That is given by x1 or x2. And closure or clean star is 0 or more occurrence of a symbol from a language, right? It may be an empty string. If you are giving L star, it may be an empty string if it is 0 occurrence of a symbol. If it is 1 occurrence, means it will be a language L, right? If it is 2 occurrence, it will be LL, right? 2 times, right? Similarly, it goes on. So that means you are concatenating L itself for k number of times. Now we are going to see how to check whether the string is accepted by the language or not. For that, we are going to write an algorithm which will accept a string if that string is available in that language, and it will produce an output 1. if that string is not available in that language, it is not accepted means then it will reject the string and it will give the output as 0, right? So the language accepted by an algorithm is a set of string which is formed by the 0 or 1 for the given example, and it will give the output a of x is 1. Otherwise, it will give a of x is 0, right? So we have to check that we can tell that the language L is decided in polynomial time by an algorithm A if there is a constant k such that for a given string x of length n, the algorithm correctly decides and produces answer in the time of big O of n to the power k, where n is the length of the string, right? So if it can give the output in polynomial time with respect to the length of the string, then we can say that language is decidable in polynomial time. So to verify this, whether it is decided in polynomial time or not, we are using a verification algorithm, right? So this verification algorithm, A is having two arguments. One argument is the given string x and the other argument is a binary string y, which is called a certificate, right? So this algorithm verifies the input string if there exists a certificate y such that a of x comma y is equal to 1, right? So the language verified by the verification algorithm is given like this. It belongs to 0 or 1. Then there exists a y which belongs to 0 or 1 such that a of x comma y is 1. Let's say language reducibility. So here let's take two problems, L1 and L2, and I have to solve the problem L1. For that I have to write an algorithm A1, right? Instead of writing algorithm A1 separately, I am going to use the algorithm A2 which is written for language L2. Let me take this algorithm A2, but what is the input for this A2? It is in the form of a string which is required by language L2. So what I have to do is the input x for the language L1 is given to a mapping function or the reduction function f, which will convert this input x into the form of f of x, which is belonging to L2 form, right? And then this input is given as given to this algorithm A2. This is if this is a deterministic or deterministic polynomial time algorithm. It will produce the output s in case f of x is accepted by L2, and it will give the output as no if f of x is not belonging, it doesn't belong to L2, right? So all this A2 will produce this output in polynomial time, and this output will be taken as the output for this algorithm A1. So if f of x is belonging to L2, it will produce s. The same will be considered here, and now the A1 will give the output as x belongs to L1. If A2 produces the output as no, A1 will give that output as no. That means x is rejected by the language L1. That is, x is rejected by this algorithm A1. Okay. So algorithm A1 decides whether x belongs to L1 by using mapping function or the reduction function, and the algorithm A2 which is used for language L2. This is known as language reducibility, and now we can say that L1 is polynomial time reducible to language L2. We can represent this as L1 polynomial time reducible to L2, or in reverse versa we can write it as L1 reduces to L2 or L1 reduces to L2 if and only if there is a way to solve L1 by a deterministic polynomial time algorithm using deterministic algorithm that solves L2 in polynomial time. I am solving L1 by using L2's algorithm. Okay, so we can write it as L1 reduces to L2 in this way, or L1 polynomial time reducible in case if it can be done in polynomial time, right? So let's see. Different complexity of type problems, right? So there are 4 types we are going to discuss today. One is P-type problem. It is a class of decision problems that have polynomial time deterministic algorithm. So 3 things we have to check. The first thing is the problem nature is decision problem, and then the type of algorithm is deterministic, and what is the running time. If its running time is polynomial time, then you can say this type is P-type problem. This problem is P-type problem. Okay, and a non-deterministic polynomial time is a class of decision problem which is solvable in polynomial time by non-deterministic algorithm or non-deterministic machine, but cannot be solved in polynomial time by the deterministic algorithm. Okay, so but as we are producing the output in polynomial time using non-deterministic algorithm, we have to verify it, right? So for verifying, we need an algorithm which will run the program, which will check that whether for the given input string, whether this non-deterministic polynomial time algorithm is correctly producing the output. And if that verification takes polynomial time, then you can say that this is verifiable in polynomial time. Okay, so the problem type is decision problem, and it is not producing the output in polynomial time using deterministic algorithm, but it can produce the output in polynomial time using non-deterministic algorithm. That's why it is known as non-deterministic polynomial time. Okay, and there is a way to verify whether this non-deterministic polynomial time algorithm is correctly producing the output or not by using one polynomial time deterministic algorithm. So this non-deterministic polynomial time algorithm is a superset of P-type problems. That means out of all the problems in NP type, some of the problems are checked and found that some of the problems can be solved by deterministic algorithm, and it's being categorized as P-type problem, right? So P problems, and difference between P and NP problems are, it is a set of problems which can be solved in polynomial time by pure deterministic algorithm. Here, it cannot be solved in polynomial time by deterministic algorithm, but can be solved by non-deterministic polynomial time algorithms. And this is verifiable in polynomial algorithms. Here also, this can be verifiable, even though you cannot obtain in polynomial time, but if the solution is given, it can be verified in polynomial time. P problem is a subset of NP. Here NP is a superset of P. All P problems are deterministic in nature. Here it is non-deterministic in nature. Example, linear sort and all we can take. But here for NP problems, we can take TSP, knapsack problem. Let's see some more problems here. The decision problem, NP problems are decision problems. It will give the output yes or no. And three algorithms I have discussed here. One is graph coloring. Here we have to check whether is there any way to color these nodes or the vertices in alternate ways. That means no two adjacent nodes have the same color, right? Is there a way? You have to tell whether it can be possible or it is possible or not, right? So this is graph coloring problem. And second one is click, right? For a given graph, we have to select a subset of vertices which will make a complete graph, right? So normally the given graph may be complete or incomplete. If the graph itself is a complete, the maximum size of the click is the number of vertices itself. But in case if the graph is not a complete graph, we are trying to find out whether if you take a subset of the vertices and if it makes a complete graph, then that is known as a click. And the size of the click will be taken as the number of vertices which forms a complete graph. Right. So for this example, 1, 2, 3, 4, 5. So this 5 vertices forms a complete graph. So this click size is 5. Right. And the third problem is a satisfiability problem. And here we are going to take a Boolean expression and check whether this Boolean expressions will give the output as 1 for the different truth values for the assignments of values for these variables, Boolean variables, right? So here there are two variables x1 and x2, and if you assign the values 0, 1, 0, 0, 1, 0 or 1, 1, all the 4 combinations, you are trying to find out whether it will give the output as 0 or 1. If it produces the output as 1, then you can take this as a satisfiable one. If it cannot produce output for all the 4 combinations, then you can say this is a unsatisfiable problem. But now we have to check whether all these problems which are solved by non-deterministic algorithms can be verifiable by polynomial time algorithm. That means for each and every deterministic algorithms, we have to write an algorithm which verifies whether it is giving the output in polynomial time, right? So this is different from finding the solution in polynomial time. You are just going to verify whether it is giving the correct or wrong. The answer what it's giving is correct or wrong in polynomial time. Okay, so let's see in the next category, NP complete problem. So this NP complete problem is a type of problems for which we are yet to find the solutions by using both deterministic as well as non-deterministic algorithms. It is very hardest to solve, so it comes under NP hard problem, that is which is the next type of problem. So NP hard problem is a problem for which it is a type of optimization version of the problems. All the optimization problems comes under this, and it is not just only give the answer as yes or no, but you have to find optimal solution for that. And out of these problems, NP hard problems, some of the problems can be verified in polynomial time. That category is known as NP complete problem. So the difference of this NP hard and NP complete is given here. A language which satisfies the property P2 is known as NP hard. That is the property. If a language is producing a solution and using some algorithm, if that algorithm is used to solve all the other problems, that means if L is used to reduce to all the other languages or all the other problems which belongs to NP, then you can say this is NP hard problem, right? But it is not necessary for that problem to belong to NP, right? So that is what NP hard problem. Okay, but in NP complete problems, it takes the hardest part from NP hard. That means you cannot find solution both by using deterministics as well as non-deterministic algorithm, but there is a way to verify it using reducibility, language reducibility. So that's what given here. It's a type of NP problem, but you are yet to find solution using either deterministics as well as non-deterministic algorithm. That means no one proved that no polynomial solution, no polynomial time solution exists for NP complete problem. But we can verify it using language reducibility. So the different complexity classes are displayed here. So there are 4 types of problem. The first category is polynomial time problem. So here it can be solved by deterministic algorithm in polynomial time and can be verifiable in polynomial time. In the case of NP type, here it can be solved by non-deterministic algorithm in polynomial time, but it can be solved in deterministic algorithm in exponentiation form or some other non-polynomial time, right? But there is an algorithm to verify it, verify that non-deterministic polynomial time algorithm in polynomial time. Okay, and in NP complete problem, here we don't have any algorithm which is solvable in polynomial time, but it can be verified by polynomial time algorithms, that is using language reducibility. And in the case of NP hard problem, there is no algorithm which can solve these problems in polynomial time, right? There are solutions, there are algorithms to solve this problem of NP hard, but no one is producing the output or no one is having the running time complexity in polynomial time. It may be in exponentiation or factorial form. But in the case of verifiability of this algorithm, here also we can achieve verifiability using language reducibility as done by NP complete problem. But here it is not necessary to be coming under an NP type. So this is either verifiable by polynomial problem or it may not be verifiable with polynomial time problem. So this NP hard is different from NP problems in that verifiability part. Stephen Cook and Leonid Levin states that the satisfiability problem is in P-type problem if and only if all P-type problem is equal to NP-type problem. That means let's see what is satisfiability. Already we have discussed that Boolean expression. A Boolean expression will produce an output 1 for all the for any one of the combinations of the variables present in that means, then it is known as satisfiable one. And if for all the combinations, if it produces 0 only means, then it is known as unsatisfiable one. So for checking that, to solve that problems, we need to check all the 2 to the power n combinations of variables. So it always produces the output in 2 to the power n, that is exponentiation time problem. So there is no deterministic algorithms which will solve this satisfiability problem in polynomial time. But there is a chance to have a non-deterministic algorithms which can solve the satisfiability problem in polynomial time. So once if it is solvable in polynomial non-deterministic polynomial time, then it will come under the category of NP type. So if you want to make satisfiability is in P type, then only it is possible only if you make all P type is equivalent to NP problem. Also Cook states that a problem is NP hard if and only if all the problems are reduced by satisfiability problem, or you can say this satisfiability problem is the base problem. Using this problem, if you can reduce all the other problems, then that problem is known as NP hard problem. Okay, and also we can prove SAT is in NP complete problem. That means if any problem in NP can be reduced in polynomial time by a deterministic Turing machine to the problem for determining whether a Boolean formula is satisfiable. That means, for example, if you are taking subset problem or click problem, if you are representing that, if you are using that problem to solve this Boolean formulae and make which is satisfiable one, then you can say that problem as NP complete problem. Okay. So that means every NP problem reduces to SAT, means it reduces to SAT, that is satisfiability problem. Thank you. So let me summarize. So 4 classes we have discussed: P type, NP complete and NP hard problems, and Cook's theorem for satisfiability. We will see the satisfiability problem in the next video. Thank you.